All right, well, good evening, everyone. It's a great pleasure to be here. My name is Mike Seifert, K6STR, Kilo 6 Sierra Tango Romeo. And I'm going to talk tonight about space telescopes, astrophysics, and deep space communication. Now, that's a big topic, several topics. So I'm going to divide this into three parts, or two parts, really. Space telescopes and astrophysics first, and then deep space communication after that. My specialty over the past 27 years at JPL is astrophysics, but since this is a ham club, I thought I'd talk about radio communications, how we talk to spacecraft, how that's similar, how it's different from ham radio. But first, we're going to talk about space telescopes and astrophysics. So one of the questions that people in Western civilization and all across the entire globe have pondered for thousands of years is, what is the universe made of? And related questions like, is it unchanging? Is it infinite? This is a portrait from the 16th century of the Greek philosopher Plato, who in one of the first cosmology books, the Timaeus, written in 360 BC, asked these same questions. Is the universe infinite? What is it made of? And he speculated that the universe was made out of 5 elements: fire, earth, air, water, and this fifth element called ether or quintessence, depending on how you translate it. And he associated those 5 elements with the 5 regular polyhedra, which are shown here. Our modern view, of course, is quite different, but he used reasoning and philosophy to arrive at his first ideas of what the universe is made of. Now we can fast forward almost 2,000 years to the time of Galileo, the famous astronomer. And he used a very modest telescope. This is about a 1 meter long telescope. It's about this big around. Anybody with a good pair of binoculars or anybody with amateur astronomy interest, you have a telescope that's better than what Galileo had. But with this very modest telescope, he discovered our moon has mountains. Jupiter also has moons, and the moons of Jupiter orbit Jupiter, not Earth. Venus has phases, just like our moon has phases. And Venus orbits the sun, not Earth. The sun has sunspots, and it rotates. And the Milky Way, that's what you see when you go out on a dark sky night. You see the Milky Way up there. They didn't know what that was. Galileo discovered that that is composed of stars like our sun. So Galileo was famous because he brought new technology, new instruments, and observations to science in a way that was just really revolutionary. And of course, he got into a little bit of trouble for it as well. But let's now fast forward to the 1920s. So we can build bigger telescopes. This is the 100-inch telescope at Mount Wilson. Mount Wilson, sadly, is not a SOTA summit. The SOTA summit is Occidental Peak, which is a little bit of a bushwhack away from Mount Wilson. This is a 100-inch telescope, just quite large. You can go for tours of the telescope facility and see it. That telescope is famous for one really big discovery, lots of discoveries, but one really big one was the expansion of the universe. So the portrait just to the right here is Edwin Hubble, who used that telescope to look at galaxies. Now, a galaxy is a collection of stars. We live in a galaxy, the Milky Way galaxy. It has about 100 billion stars in it. We also have nearby galaxies. He used that telescope to look at nearby galaxies and was able to estimate their distance and estimate their velocities. And what he discovered was that those nearby galaxies were moving away from us. And the farther away they were from us, the faster they were moving away from us. And the interpretation of that data, this is his 1929 paper, this is the plot from it. The interpretation is that the universe is expanding. Something that I'd like to emphasize is that science is cumulative. So we build on the knowledge and discoveries of others. And in this case, Hubble built his conclusions on the key work from Henrietta Leavitt, who previously discovered a relationship between stars' brightnesses and other things that made Hubble's work possible. So maybe you've heard of Hubble in a different context. This is a picture from the Hubble Space Telescope. The Hubble Space Telescope was named after Hubble for a specific reason. One of the key projects of the Hubble Space Telescope was to examine that expansion of the universe and try to measure it more accurately to higher distances. Does it still hold? Is it still accurate? Can we really put more decimal points on the expansion of the universe? So that's what the Hubble Space Telescope was built for. But of course, it discovered a lot of other things along the way. This image is kind of striking, and I'm showing this particular image to make a couple of points. So this is an image of what we call a cluster of galaxies. It's a bunch of galaxies in a large group that are gravitationally bound to each other. And if you look here towards the center, you can see these long, thin arcs. So those look kind of funny. What are those things? Those are distant galaxies, galaxies behind and further distant than this cluster of galaxies. And they are being magnified and distorted by the gravitational effect of the cluster of galaxies in the foreground. And so this is something that Einstein predicted. There's also a prediction of regular gravity, that gravity can bend light. That's what's happening here. But there's a funny thing about this, which is, okay, we have a bunch of galaxies. We have stars in them. We know approximately how much a star weighs. We know how many stars are in each of these galaxies, approximately. So we can calculate how much bending of light should happen from this cluster of galaxies. And it's not nearly enough to do this effect. So this was one piece of evidence for something we now call dark matter. Dark matter was postulated earlier in the 50s, but with the Hubble Space Telescope and other measurements, the data just became more and more convincing. And that's why many physicists and astronomers today believe that a large fraction of our universe is made up of what we call dark matter, a mysterious substance that interacts gravitationally, but we have not yet discovered in the laboratory. There's another piece of evidence for dark matter here, and that's that if you measure the galaxies here, you can see with other instruments, you can tell how fast each of the galaxies is moving. And it turns out they are moving around their common center of mass. And you can calculate, again, how much mass would it take to keep all of those galaxies in orbit. And again, that mass is not enough, just counting up stars and galaxies, to account for that orbiting. And again, if you postulate the same amount of dark matter that it took to do that gravitational lensing, you would get the same conclusion. And there's further evidence. If you take another space telescope called the Chandra X-ray telescope, this can take pictures of galaxies in X-rays, and you get a big hot spot in X-rays at this cluster of galaxies. And it turns out the interpretation of this is that there is a very hot, very thin gas in this cluster, and this gas is glowing, and it's not just glowing red hot or white hot, it's glowing X-ray hot. Even though you can't see the gas in the visible images, with X-ray instruments you can see the glowing gas. And this gas is hot enough that it would just fly apart under the thermal pressure if it were not for a significant amount of mass in the cluster of galaxies. And again, you can calculate how much mass does it take to keep that hot gas from flying apart. And it's not enough in just the stars and galaxies. You have to have an extra ingredient of dark matter to hold that gas together. So that's Hubble. That's the Hubble Space Telescope. That telescope, the Hubble Space Telescope, was also used to do that key project. One of the things that they tried to do is measure galaxies at farther and farther distances using something called supernova. A supernova is an exploding star. It's a good way to tell how far away a galaxy is. As we measured galaxies farther and farther away, it turned out that instead of just a simple expansion, it looks like over the past many billions of years, that expansion rate is slowly increasing. We call that acceleration. So our interpretation, as astounding as it is that not only is the universe expanding, that expansion is speeding up over cosmic time. And because of the convincing data that was discovered for this one plot is maybe not super convincing, but many lines of evidence, which I won't go into here, came to the same conclusion. Saul Perlmutter, Brian Schmidt, and Adam Rees received the Nobel Prize in Physics in 2011 in recognition of this astounding thing. So what about this acceleration? How can we think about it? How can we explain it? Well, the astonishing answer is that it appears that there's an extra repulsive component to the universe. And our understanding is really very minimal of this. We've given it a name. That's the main progress in the field. We call this dark energy. That's not a particularly illuminating name. It's not a very explanatory name, but it's a name. And I would say now the jury is still out. Is there an extra unknown substance in the universe? Are Einstein's theories of general relativity slightly wrong in some way? The answer to those questions is still unknown, and that's one of the reasons why we're building space telescopes. So I started out the talk with Plato's question of what is the universe made of? Well, here's the pie chart for what we think of today. We think that the universe on the largest scales has a big component, over 75%, that's dark energy. A big chunk of it is dark matter. A smaller chunk is hydrogen and helium gas, including that hot glowing gas I showed you. Only a small sliver is stars. And the people in this room, everybody watching the presentation, this building, our Earth, it's only a tiny, tiny sliver on this plot. So how can we try to understand dark energy better? So this is one of the big mysteries in physics today. So we're trying many things to try to measure dark energy better, measure the expansion rate and the acceleration even better. The discovery was done with supernova, looking at galaxies further away. And I'll mention briefly two other techniques that we're using today. One which makes use of gravitational lensing, and one which makes use of what I call galaxy clustering. That's how galaxies are distributed throughout the universe. So this is a picture now from the Euclid Space Telescope. This is something that I've spent the past at least dozen years working on. This is a picture again of a cluster of galaxies, and again you can see those arcs reminiscent of the distant galaxies being lensed by the mass. We call that strong lensing, when the lenses are really disturbed, really big arcs that are very plainly visible. Well, it turns out that this is pretty cool, but these are kind of special objects. They're not everywhere in the sky. They're just in very specific places. Throughout the sky, we can use something called weak lensing, which is just a much weaker effect that you can really only detect statistically, not so easily with your eye. And what we do is we break the universe into different slices at different ages. The further away you look, the further back in time you're looking, because the speed of light is not infinite, so it takes light a while to get to us. So things that are further away, you're seeing them as they were, in some cases, billions of years ago. So we're using gravitational lensing to break the universe up into slices, see how clumpy it is at different ages, and then see how that clumpiness changes with time. And that clumpiness depends on the interaction between the gravitational attraction of regular gravity and the repulsive force of dark energy, and how those balance govern the properties of both dark energy and dark matter. Another approach that we use is illustrated by this picture from the Sloan Digital Sky Survey. This is a map of the locations of nearby galaxies. So in this picture, we are in the center. The galaxies furthest away from us are on the perimeter, and stuff in between is in between. It's wedge-shaped. This is a two-dimensional slice, and it's wedge-shaped because we're only seeing part of the sky in this. But one thing jumps out at you, perhaps. The galaxies in this picture have kind of a filamentary or foamy look to them, like a sponge or something. They're not what I would say randomly placed. And again, the way that galaxies form, the attractive force of gravity and the expansion of the universe, the interplay from those govern the statistical properties of that foamy structure. And that's another way that we can measure the properties of dark matter and dark energy. This picture is from the Sloan Digital Sky Survey. This is, at its time, a groundbreaking telescope based on the ground, a 2-meter telescope, rather modest, but instrumented very sophisticatedly. But Hubble and also the Sloan Digital Sky Survey, those older generations of instruments were and still are limited. In order to measure the properties that we are interested in better, we need to cover more area of the sky to greater depth. And to do that, we need telescopes that have a larger field of view and also are very sensitive. This picture here, we've got a picture of the moon. And these blue squares here represent the field of view of the Euclid Space Telescope, which I'm going to tell you a little bit more about in a second. That little black square down here, right here, that's the field of view of the Hubble Space Telescope. So although the Hubble Space Telescope has a larger light collecting capability, Euclid can survey the sky and measure more galaxies much more quickly because of a number of features of how it's designed, but also largely because of its very large field of view. So this is a computer rendering of the Euclid Space Telescope. It's about 1.2 meters in diameter compared to the Hubble Space Telescope, which is about twice the size. And it has some features that allow it to measure large areas of the sky very quickly. The project was run by the European Space Agency. It has contributions from countries and space agencies all across Europe, also Japan, Canada, and a big contribution from NASA, in which I participated. This is the first space telescope for a space mission that was specifically designed to try to measure the properties of dark matter and dark energy in more detail. It was launched from Cape Canaveral in Florida on a SpaceX Falcon 9 Heavy, July of 2023. Its early observations showed that it was working well. It takes a while for the telescope to get from launch to low Earth orbit out to its eventual orbit. I'll say a few words about that in a second. But basically the way this works is it takes a picture with that large field of view that I showed, steps over a little bit, takes another picture, steps over a little bit, takes another picture, and repeats that process over and over and over again for about 6 years. So over that 6 years, it'll cover about a third of the sky. So the way to think about this is that with Hubble or some of the other space telescopes, it's like taking a tiny straw and trying to look at the sky. Euclid is a little bit bigger and very fast at covering it. Even with the higher speed, it still takes 6 years to cover a third of the sky. So one of the keys is the larger field of view. That's done with a new to space telescopes telescope design. This is something called a 3-mirror Korsch anastigmat. It's a fancy name for a telescope that has 3 curved surfaces that obey a certain mathematical relation. If any of you here are amateur astronomers, you might have had a Newtonian telescope that has 1 curved surface. You may be familiar with Cassegrain or Schmidt-Cassegrain telescopes that has 2 curved surfaces. Hubble has 2 curved surfaces and a corrective plate. This has 3 curved surfaces, and that's the key to having a very wide field of view. The primary mirror is a big thing with a hole in the middle of it. The secondary mirror is off to the right in that computer picture. And the third curved mirror is buried inside the instrument. The third curved mirror is is shown on this off to the left. There's a number of folding flat mirrors that just steer the light around. So inside the instrument cavity, there are two instruments, one that works in the visible, one works in the infrared. The visible instrument is sort of a massive array of detectors. It has about 100 to 200 times as many pixels as a modern iPhone. So this is a sort of a state-of-the-art astronomical instrument for space. The detectors are operated at a very cold temperature, 150 Kelvin or so. That's about minus 184 Fahrenheit. Kelvin is degrees Celsius above absolute zero, so very cold temperature. That minimizes the extra noise that might come in from thermal electronics effects and detects effects within the detector. There's a bunch of sophisticated readout electronics and other things that make this work. The near-infrared instrument is shown here. That's 16 detectors. These are near-infrared detectors, so this is light that's at longer wavelengths than your eyes can see. The detectors themselves were fabricated by Teledyne Imaging Systems just down the road in Camarillo. I think maybe we have Gary here worked on these in the past, and maybe there's a few of your friends or neighbors who had a role in this as well. The detectors are operated at very cold temperatures as well, in this case about 100 Kelvin, 100 degrees above absolute zero, with some fancy readout electronics that are also operated at cold temperatures. There's a number of filters and other equipment that go in front of this that I'm not showing. This is the part that NASA provided to the European Space Agency. So a combination of Teledyne, NASA-JPL, NASA Goddard Flight Space Center, and a number of other private contractors worked on this together. And all of that really resulted in a number of beautiful images. If any of you are into amateur astronomy and like image processing, all of the data that I'm showing you today is available publicly. You can download it, you can do your own color scale, you can process it however you like. Many amateurs have done this to bring things out, and there are other ways for amateur astronomers to get involved in this as well. So I'll go through some of these. The first thing to say, I guess, is with this very wide field of view and very large coverage of the entire sky with the Euclid telescope, we get our most statistical power on measuring the properties that we're interested in by measuring billions of galaxies. Many of those galaxies, or most of those galaxies, are relatively low signal to noise and are just little smudges, so not very interesting to look at all. So instead of showing you a bunch of pictures of little noisy, fuzzy blobs, which are not very interesting, I'll show you some pictures of some of the more interesting objects that we saw along the way, because I think it's more exciting. The picture here on the right is the Perseus cluster of galaxies, a nearby very large cluster of galaxies. This picture, I don't expect you to count, but there's roughly 100,000 galaxies in this image. And one of the things that we were doing this, the big galaxies in here are visible from the ground and have been known before. But one thing that's hard to do from ground-based telescopes, even very big ones, is to accurately count up the properties of what we call dwarf galaxies. Dwarf galaxies are very small compared to the Milky Way. They're fainter than the Milky Way. They are more numerous than the other galaxies here, but they're not brighter and they don't make up most of the mass. But understanding how many galaxies there are at different masses, how they evolve over time, is one way that we learn about the universe and how galaxies evolve. This is a picture of the Horsehead Nebula. This has been studied both from the ground before and also from the James Webb Space Telescope, also from the Hubble Space Telescope. Those previous observations have been of limited regions around that Horsehead, the really famous and distinctive little feature right there. One of the things that Euclid can do is to try to answer what's been a long-standing question, which is, we know stars come in different sizes, different masses. Our sun is kind of a middle-of-the-road star. There are ones that are much bigger, so there are some that are much smaller. how much smaller do they come, and how many are there that are that small? How does the universe make stars? How are their sizes distributed? With this picture, we can start answering some of those questions. So above this fancy-looking horse head, there's a region where the new stars have been formed, and there are some objects that are smaller than stars. Some people call them free-floating planets. Some people call them substellar objects. And Euclid is, because it has such a wide field of view, can start identifying rare things like that in large fields of view. And that's one of the things that's useful with Euclid. Once you've found something that's unusual, it's almost always better to follow it up with the James Webb Space Telescope or the Hubble Space Telescope or some of our more powerful facilities that do not have a large field of view but have a really sensitive array of detectors. Okay, I'm going to show you a quick video. This is a video made by the European Space Agency to summarize some of Euclid. So I'll stop it here for a second. So many of you are familiar with a globe of the Earth and a map, a two-dimensional map that you might see on a schoolroom or on your ham shack. It's got the whole world on it. So this is a map of the celestial sky projected in 2 dimensions. The center of our galaxy is in the dead middle. The galactic center is in the middle. The north galactic pole is at the top. The south galactic pole is at the bottom. Those 2 blobby things at the lower right are the large Magellanic and small Magellanic clouds. They're not visible from Camarillo, but they're visible from the southern hemisphere. So that's, just to orient you, that's the full sky. Okay, so we're going to keep moving along here a little bit. So the region that Euclid is going to cover over 6 years is highlighted here in this kind of orangey beige color. That's about 1/3 of the sky, and we've chosen the regions that are outside of the plane of the galaxy. This is where it's easiest to see into deep space. So I'll keep moving. So Euclid is only a little ways into its study, so we're going to show you 1% of the full survey. That's data that's been processed and released now. And we're just going to zoom in and keep zooming into this region to show you sort of what the dynamic range and the images look like as you go through all of this. So this is 1% of the full sky, and we'll eventually get to about 33% of the full sky. So we'll keep zooming in, and as you zoom in, instead of just seeing pixels, you keep seeing more galaxies because Euclid is covering a lot of sky and with a very sensitive array of detectors with a lot of pixels. So this is a little group of galaxies that are off in this one part of the sky. It's a cluster called Abell 3381. And we'll just keep on zooming in. And we'll keep on zooming in. And we'll keep on zooming in. And you can see there's these very distinctive large spiral galaxies, but there's also little, you look to the sides, you can see little galaxies all throughout this image. All over the place here. Okay, so that's zoomed in about 600 times compared to the full field. And at the end of this video, this is going to start zooming out all the way again, so you get some perspective at what that zoom really was. All right. Okay, so thank you, Isa, for that little video. I think that's pretty nice. So it's kind of a shame we can't just use our binoculars to do that or our iPhones or something. It takes a space telescope to do that. So some of the other things that you can do with Euclid, we're going to measure roughly 1 billion or more than 1 billion galaxies over the 6-year lifetime. And of order 10% of those are going to be well resolved enough that you can do detailed studies of what those galaxies look like. And this is an interesting area where there's a combination of citizen science and machine learning that's been applied to classify the galaxies. In the upper left, we have galaxies that have little bars in the middle of them. On the right, upper right, we have galaxies that show some kind of disturbed nature to them. That's probably two galaxies that have interacted in the past. On the lower left, we have classical spiral galaxies, much like our own Milky Way. On the lower right, we have edge-on disks. And so currently, the catalog has about 370,000 galaxies. You can go look at them one by one if you like. It might take you a while. If you would like to try your machine learning skills on this, you can download the whole catalog and start processing them yourselves. There's a citizen science project called the Galaxy Zoo, or Zooniverse, where we get teams of ordinary citizens who are not professionals, but have an interest in astronomy. They help us classify these galaxies, and then we compare artificial intelligence classification with real intelligence classification, and hopefully do a little bit better with the combination of the two. With a few 100,000, you can almost imagine doing that with a collection of a large number of people. With 100 million galaxies, you got to use a computer. There's no way to do that with people. I mentioned strong lensing before, so Euclid is now finding more and more of what we call galaxy-galaxy lenses. This is where there's a background galaxy and there's a single foreground galaxy and the Euclid telescope, and they're all in a line. And the background galaxy is getting magnified and distorted, and you can see little rings, big arcs, things like that. So we're finding lots of these things. We're also finding some cases where we think we have 3 galaxies in a line. This is not very likely on average, because that's a chance alignment of 3 galaxies on a single line with the observer. But with hundreds of millions of galaxies, even unlikely things happen sometimes. So this is several galaxies, or 2 galaxies being lensed by one foreground galaxy. And you can see, maybe if you squint real hard, it looks like there's one ring and then another ring around it. One spectacular example of strong lensing is from this nearby galaxy called NGC 6505. That's the big blob in the left. You can see it's a large galaxy. This is a well-known galaxy from previous studies. But what wasn't known about it was that if you zoom into the middle, you can see an almost perfect ring. And that's, again, a distant galaxy behind this NGC 6505. And the mass of this galaxy is bending the light from the background galaxy. And because their alignment is so good, the gravitational lens is almost a perfect circle. And that perfect circle, if it's a perfect circle, is called an Einstein ring, named after Einstein, who predicted gravitational bending of light. And so this is more than just kind of a gee whiz object. By studying things like this, we can, as I was mentioning earlier, really start to make models of how much mass has to be in that galaxy, how it's distributed, how much dark matter there is in order to produce that precise shape. And if we do this with not just one object, with many objects, we can start building more and more precise models of what's happening with dark energy and dark matter. Okay, so on to the second part of this talk, which is about deep space communication. How do we communicate with these spacecraft? How do we get data back from Euclid? How is that the same or different from ham radio communication? And just as a disclaimer, I should say my expertise is in astrophysics, not in deep space communication. And this being the Conejo Valley, I imagine there are people here who know as much or more about deep space communication than I do. So if you sense me stumbling, please help me out. Be happy for it. So how are ham radio and deep space communication the same, and how are they different? Okay, DX. Who likes DX? I like DX. Okay, in deep space communication, that's the whole point, right? The whole point is DX. Gain antennas. We all like gain antennas, right? Well, absolutely critical if you're going to be talking to something far away. RF power. Sometimes we like QRP. Mark likes QRP. I like QRP, but sometimes you just want to have some power. Also, for deep space communication, you want to have some power, but sometimes you're limited in what you can do. Receiver sensitivity is important for ham radio, but especially in the lower bands, we have ionospheric noise, background noise, maybe city noise. And so having the most sensitive receiver isn't always the most important aspect. So you can read a review of the radio in QST and find out what the receiver spec is, but maybe that's not the most important thing about the radio. For deep space communication, it's absolutely critical, and we go to extreme measures to improve the sensitivity, which I'll talk about. Communication modes, it's everything in ham radio, AM, FM, digital, sideband, voice, CW, all of that good stuff. Deep space communication, at this point, all digital, mostly PSK, phase shift keying, a particular digital mode. Some of you may have heard of PSK 31. This was a popular ham radio mode for a while. And it's very bandwidth efficient, and that's the reason it's used in deep space. Ham radio, we do all the frequencies. For deep space communication, that's mostly microwave. And we also, many of you have probably built battery packs. You run solar power at your field day, perhaps. So sometimes we use solar panel and batteries in ham radio, and we almost always use solar panels and batteries for deep space communication. So I said deep space, so what exactly are we talking about? So deep space usually refers to things that are beyond the moon's orbit. So how far beyond the moon's orbit, you might ask? Well, let's start with some comparisons. The Hubble Space Telescope is orbiting at about 570 kilometers. That's what we call low Earth orbit. About 2 milliseconds of light travel time. The moon is a lot farther away. It's 384,000 kilometers or so. It's over a second of light travel time or radio travel time. So you key up your radio on the moon. It takes a second before that radio signal hits Earth, just the light travel time. And anybody who's into Earth, Moon, Earth stuff, you'll know that there's a delay between the transmit and receive, just from the light travel time. So what about Euclid and JWST and some of these other telescopes? So Euclid is at something called the Earth-Sun L2 point. So L2 stands for that means the second Lagrange point. This is a quasi-stable point in space that's away from, in the direction opposite the sun, beyond the orbit of the moon, and it follows the Earth around as the Earth orbits the sun. This spot is about 1.5 million kilometers away. That's about 5 seconds travel time for radio waves or light. So this is sort of what I would call the beginning of deep space, and depending on what's happening with various resources, some people think this isn't quite deep space, some people think it is. Let you decide. You can decide, but 1.5 million kilometers is a fair distance away. We can talk about things that are farther away from that. I'm going to mention 2 spacecraft in a bit, so I'll talk about where they are. I'll start with Voyager 1. Voyager 1 is the most distant man-made object at the moment. This was launched in 1977. It's currently 25 billion kilometers away. That's almost a full day of light travel time or radio travel time from Voyager to here. This is a picture of the inner solar system and Voyager 1. On this scale, you can't really see Mars or Earth. You can see the sun at the middle, but mostly you just see the outer planets. There's another spacecraft that NASA has built called Psyche. It's an asteroid mission, and that's currently a little bit beyond the orbit of the moon at 400 million kilometers, about 22 minutes of light travel time. Okay, so I'll start at the beginning here. The first satellites in low Earth orbit, Sputnik 1 and Explorer 1. I am not old enough to have heard Sputnik, but maybe you are, maybe you know somebody who actually heard this. Sputnik, launched in 1957, was a tube amplifier. I'm going to throw up a bunch of details here on the left, so if you're interested, you can read them. I'll breeze through them pretty quickly. It was a 3-tube transmitter. You can find the circuit diagram online if you'd like to replicate it. It put out about a watt at 20 megahertz and also at 40 megahertz in a pulsed CW mode, so just on-off carrier. The first US satellite was called Explorer-1, launched about a year later. That was not a tube design. That used 20 transistors, and that was a big deal because transistors had only been invented about 10 years earlier than this. The junction transistor, which was thought to be robust enough to survive launch, was developed in 1948. So this has not been around for a while. This used about 60 milliwatts at 100 megahertz and 108 megahertz, and a second transmitter, 10 milliwatts. One was amplitude modulation, one was phase modulation, and it had some instruments on it which famously discovered the Van Allen radiation belts. Voyager 1, so I'm moving forward not in distance but in chronological age. Voyager 1 launched in 1977, 48 years in operation now, the furthest man-made object. The current spacecraft power, this is not solar power, this is not batteries, this is the decay of radioactive plutonium driving a thermocouple. And that provides electricity of about 200 watts at the moment. The spacecraft has a 3.7 meter radio dish pointed at Earth, and it transmits at 8 gigahertz, 8.4 gigahertz. RF power is about 23 watts with a traveling wave tube amplifier. Left-hand circular polarization. And its data rate is a blazing fast 160 bits per second. It's far enough away that you really cannot send data very quickly. So 160 bits is not very fast. This is faster than FT8, but not a lot faster than FT8. It has a burst mode that's a little bit faster. On the ground side, we have a giant 70-meter antenna. There are 3 such antennas scattered across the globe. There's one at Goldstone, one in Spain, and one in Australia. So one of them is available at any time in principle. So we often measure our ham radio antennas in terms of gain. The transmit on the spacecraft side, 48 dB of gain. The receive side, 75 dB of gain. That's a lot of gain when you put those guys together. Something I'm going to emphasize in a second, the receiver is made with something called HEMT amplifiers, high electron mobility transistors that make up the low noise amplifiers, and they're cryogenically cooled, and I'll show a picture of that in a second. So you can go to a NASA website called DSN Now, which tells you exactly which telescope is looking at which spacecraft, what the data rate is, where it is, what the altitude and elevation is. As I said, there's a facility in Spain, one in the desert out by Fort Irwin called the Goldstone Deep Space Network Center, and then one in Canberra, Australia. And I think JWST was operating or was downlinking data when I took this picture, but the other ones, Voyager was not. So I mentioned some of the receiver technology. This is a 26 gigahertz on the left and I think a 26 to 30 gigahertz receiver on the right. These use very low noise amplifiers. They are cryogenically cooled, and you cool them down to reduce the receiver noise in the system. In ham radio, we sometimes quote the noise figure, so maybe if you're into microwaves, you know about noise figures for your low noise amplifiers. We usually quote noise temperature for these very low noise systems. Noise temperatures for these guys are in the range of 10 Kelvin or so. That translates to 0.1 to 0.15 dB of noise figure. The one on the left here is a nicely made functioning dual feed system, I think on the Australia telescope. And the thing on the right is something I built in the lab many years ago for a radio astronomy project. Both of these have a vacuum shell that's not shown here. It's a big metal tube that goes around this. There's a big refrigerator assembly underneath that it's responsible for the cryogenic cooling. All right, so on to Euclid. So this is not as far away as the other missions, but it has some newer technology in it. It has a dish. Maybe you can see the blue thing with the blue ring around it here. That's a small dish. That's 70 centimeters. But the thing about this dish is that it's gimbaled in 2 axes. So Euclid can be off doing its survey of the sky, and the 70 centimeter dish is moving around so that it's always pointed at Earth, even when the spacecraft is pointed somewhere else. So that's important to get right. Some other facts that might be interesting for those of you who are into building battery packs or solar panels. This is 11 square meters of solar panels, 1,700 watts. That's a substantial amount of juice. But the battery is quite small. By comparison, it's 6 in series, 6 parallel, 576 watt hours of lithium-ion battery. So it's not that big, actually. And that's because this thing can put that solar panel always facing the sun all the time. The battery is really necessary for launch operations, early orbit operations. But during the normal survey, this solar panel is facing the sun the whole time, so you don't need a lot of battery. It's a 26 gigahertz transmitter, 55 megabits per second. That's a lot faster than 160 bits per second. It does this 4 hours a day, every day, 7 days a week, 365 days a year. It has some traveling wave tube power amplifiers and of tens of watts. And one thing that's new for this, it's kind of if you're into IT, the things like Voyager, it's just a bit stream, very slow bit stream, just going continuously. For things like Euclid, you're putting all kinds of files into file space on the onboard computer. You're trying to synchronize what's on the ground versus what's there and bring them down, make sure you didn't miss anything, go back for refills if something didn't transmit properly. So it uses a new file delivery protocol that's being called the FTP for space. So FTP is a file transfer protocol you may have heard of. All right, so the future. So lastly, this was launched about 2 years ago, the Psyche mission to the asteroid Psyche. This is a NASA mission that's sending a spacecraft to an asteroid. It's going to orbit the asteroid, take lots of pictures, and stream data back to us. But one of the things that this spacecraft has on it is a demonstration of deep space optical communications. So optical communications have been demonstrated from low Earth orbit, from nearby, I think as far as the moon. This is the furthest distance demonstration of this so far. At about 400 million kilometers currently, 22 minutes light travel time. It's a 22 centimeter optical telescope with a 4-watt laser pointed at Earth. It's an infrared laser, and that's beaming down a series of pulses. So this is a new, a mode that you may not have heard of, pulse position modulation. So you send a bunch of pulses, and you change where in time those pulses are, and that's your encoding of your ones and zeros for digital information. Max data rate of 267 megabits per second. It's lower than that now because it's further away. But this is sort of, high-speed Wi-Fi or high-speed internet type speed, not the 160 bits we were talking about earlier. And this was being developed in order to really be able to deliver more information, more data back to Earth from some of these deep space missions. One cool thing about this is that it has a point-ahead transmitter. And so if you've ever done microwave, one of the things that you do with microwave is you do some beaconing where you broadcast a tone and somebody, they tilt their receiver to kind of maximize the signal, and then you try to start your QSO based on the alignment. You can't quite do that here. What you have to do is the ground side transmits a laser beacon, you line up on it, and then you point ahead, because when you transmit your information back to Earth, you don't point at where Earth was when you received the signal. You need to point at where Earth is going to be when the signal hits Earth. So the signal is smaller or the beam for this is smaller than the size of the Earth. I think it's several hundred kilometers. So this has to know where Earth is going to be when the laser beam hits Earth. That's kind of cool. On the ground side, the uplink data and beacon is at Table Mountain. If you are a SOTA operator, you may have activated this summit, right? So that's a SOTA summit. There's a 1 meter telescope up at that facility with a 5 kilowatt laser, and that's sending commands up to this thing. The downlink is to the 200-inch telescope at the Palomar Observatory, also nearby SOTA summit. And the receiver here is based on some new technology, superconducting nanowires. These are single photon detectors. Basically, you have a superconducting wire, a photon hits it, it slightly changes the inductance of that wire. You have a sensing system that senses that change in inductance and registers a little blip for that photon. So you can count very high rates very accurately with this kind of technology. So I'll kind of wrap things up here. So in conclusion, I'd like to say that looking back at the start of this talk with the picture of Plato, where we started with, what is the universe like? Here we are trying to answer those questions with new technologies and new instruments that open our eyes to new views of the universe. Some of the startling discoveries that we've made along the way, from Hubble to Perlmutter, Rees, and Schmidt, who discovered the acceleration or dark energy. These are just fascinating discoveries. We don't fully understand them. We don't know whether Einstein's theories about general relativity are exactly right, whether they need a small modification, or whether there are new components to the universe that we haven't measured yet. So Euclid was designed to try to make progress on those questions, but of course, it will also make other discoveries on the way because it's a powerful telescope. Also, each space mission helps build the future. So you demonstrate some technology on one mission, you do a bit better, or reuse the parts that were good, do better on the next mission. And science is cumulative. We learn from the past, and we make progress in the future. And I think this will be an exciting journey. And I'd like to acknowledge all of my colleagues at JPL in the Euclid collaboration, at various data centers, and at the European Space Agency. This is a tremendous project with lots of people around the world working on it together. Thanks.